blue Samsung phone that we found, and we know the name of the person that owns it because their wife called. They're looking for you. But if you're looking for your phone, we have it at registration.
Great, thank you. Right, I've got the mic, I've got the slides. This is going to be about a scientific paper that scooped another scientific paper that we wanted to write, and how we basically got back at it. I'm Sergey Bratis. I'm a research assistant professor at Dartmouth College. This is Anna Shubina. She is the math brains of the operation. There's also a student who actually did all the work, as it goes, Chrysil. He unfortunately could not make it today, but we'll go through his part as well. And with that, let's start it off.
So, we're from New Hampshire. We're actually from a metropolitan area of New Hampshire, and we have a picture to prove it. Over there on the left. So, New Hampshire is known for having a lot of snow, more snow than Washington, D.C., a lot of hills, and a lot of old clocks, and the kind of clocks that don't synchronize with a master clock far, far away, which is just as well because hills generally interfere with radio signals. We have a lot of places where it's really hard to get any kind of wireless connection to anywhere because the only important point that you can get any line of sight to is the sky. So this is the clock of the Baker Tower at Dartmouth. This is the Baker Berry Library down below. And there is folklore which says that this clock, that the keeper of this clock used to synchronize it with the Dartmouth website by looking at the time on the website, and that the keeper of the Dartmouth website used to set the time on that website by looking at the clock. I don't know if this is true. So, clocks. Old clocks, as most of you probably still remember, tend to drift away from the actual time over time. So they would drift away like 5 minutes per week or something like that per month. They all have different deviations from the real time, but generally we don't get to find out what those deviations are precisely because they don't talk to anything pretty much.
And it turns out that the modern clocks are really no better, except the deviations are in microseconds, mostly. But they are on the microsecond level. But they're really consistent about those deviations. And there are several researchers who actually noticed this and made a really interesting fingerprinting work based on that. Tadayoshi Kono, Andrei Broido, and Casey Claffey. And they started out this entire vein of exploration with fingerprinting individual devices based on their clocks. And so we're going to cover that. But in 30 seconds, this talk is really about using clocks for fingerprinting devices, using clock skews. And the thing about clock skews is that they're there for the asking or for the listening, especially in 802.11 where the timestamp goes in every beacon frame. So you can just sit there and look at your device and look at your beacon frames and fingerprint the devices that's been sending them. And people worked out how to use them, and that's actually where we're scooped to. But we got back at them because we figured out how to spoof them for 802.11 APs. And finally, we're going to talk a little bit about how to detect that sort of spoofing. Okay. So, and this is my official New Hampshire hat. When I heard about the snow here, I figured, yeah, I'll bring it. I'm not going to change. I'm just going to fly like this and step off the plane in it. Except, of course, the plane got canceled. We had to take the train.
We didn't bring our truck. This would have probably been the only car.
Yeah, that's right. Yeah, we're missing that. Okay. So, the thing about clock skews is that they are tiny but consistent. And Anya, who's the math part of this effort, will explain how you can actually find them out and graph them.
Well, in the ideal world, all clocks would be perfectly synchronized. In the real world, if you take your reference clock and you graph the other clocks, the time shown on other clocks with regards to that clock, you are going to get something like this. They will all be different. They will be they will be close to, the lines will be close to being straight lines at 45 degrees, which you cannot see on this picture.
You cannot do that. Macs are not our favorite machine.
So you graph the times of other clocks with regards to the reference clock, and you compute the slope by taking the time that another clock runs through. The time in the other clock is going to be delta y when the time is going to increment by delta y when the time in our clock increments by delta x. And the clock skew is defined to be the slope of this -1, because the slope itself is going to be really close to 1. So if you go and graph it, if you go and graph the real numbers, for the colorblind people here, those are actually two graphs. They are so close that they seem to be almost 1. One is green and one is red. So those are points from
one line.
this.
I'm of course colorblind.
Yes. So the time from our reference clock is on the x-axis, and those times are on the y-axis. And we're going to, instead of graphing those actual times, we're going to graph the difference between them and the time in our reference clock, because this will let us get the precision that we need. So if we subtract the time on our reference clock from the time on those clocks, and if we take the results in microseconds, this is going. You can see that these two graphs are different.
Yeah,
the red one is actually different from the green one. So these are graphs of times on two different clocks with the reference clock time subtracted. So we just fit the line to the clock, to those points. The slope of that line is defined to be the clock skew. And in parts per million, the actual clocks have this skew in parts per million.
Right. So just in case you haven't noticed, these are real clocks. And so this little trick lets us actually see that these are two different lines. And they're actually the Linksys that we've got on the lab. So you can see what the clock skew is in real life. Something like 6 or 7 or 10 parts per million. 10 to the -6, but of course we're going to use this ppm because the superscripts in PowerPoint are way too much work. Anyhow, so who came up with this? Who came up with the observation and used it? Tadayoshi Kono, Andrei Broido, and Casey Claffey in 2005 published this paper on remote physical device fingerprinting. And what they noticed is that different devices had different skews, and those skews just kept consistently at the same levels for different clocks. So you could actually tell a clock by its skew. And the way they did that, they sent ICMP timestamp requests, and they also used TCP timestamp options, type 13, option 8, type 13 code 0 in ICMP. And being very accurate computer scientists, statisticians, hackers, they posed the question very carefully. the question that this fingerprinting was helpful in answering. Namely, if you ask two hosts for their clocks and compute the time skew, are they the same hardware clock? So this is useful when you need to tell two devices that might be one virtualized physical device from each other. And also, this is probably going to be very useful in mapping the clouds, which are all virtualized platforms. But so we haven't seen any people exploring that, but that's definitely something that's going to come up. And it turned out that the clock skews were so consistent that even the network latency could be diffuted with some proper statistics. And this is what the real-world clock skews from their paper, measured on a cluster of desktops, looked like. So you see the hosts ordered by the, okay, help me out here.
By the lowest skew they measured within 12 hours.
So they are arranged by the lowest skew measured within 12 hours, and the height of the bar is the deviation over that time that they observed. Because, of course, the clock skew itself varies a little bit based on things like the temperature, possibly, or maybe power consumption, or maybe any one of those things that you can imagine can affect the physical clock. So the clock skew itself is subject to variation. But even so, you can definitely tell one of the computers on the left from one of the computers on the right. And so, you know, come 2008, we were thinking, well, beacon frames are transmitted 10 times a second, and they have this microsecond clock, and that clock is on the RF interfaces chip. So it's the crystal on the actual card. And this is great because we can just sit there and listen, and we can try to fingerprint the APs. And we said that that's what we're going to do during our talk on fingerprinting access points by throwing garbage frames at them. And guess what? A couple of weeks later, we see this paper by Jana and Casera, published in the scientific conference Mobicom. And it's called On Fast and Accurate Detection, Unauthorized Wireless Access Points Using Clock Skews. And I go like, darn, scooped. Anyhow, but we start reading this paper, and it turns out that, you know, yeah, they can tell an access point from another access point. Presumably, they can tell an access point that is your laptop with one of those cards that let you go into master mode. But they say, this is really good. This is really fast and accurate, and this is really hard to spoof. Here is the timestamp in the beacon. This is what, you know, you'd be able to see it in its 64-bit glory. You know, if you could do that sort of thing, it could be useful, because imagine most of the time you've got a situation when you come in, you open up your laptop, you see some beacons, and the access point that you start dealing with based on what you see in these beacons, even if you do the crypto authentication, that's actually an evil twin kind of a laptop. And you think that crypto protects you, but not so. Crypto is complex, parsing complex data is hard. You start parsing complex data way before you can do any meaningful crypto, and this is your owning a MacBook in 60 seconds talk by Jenny Cash and David Maynard, and then the month of kernel bugs, and there is no driver out there that can be completely relied on to accept complex data and not screw up when parsing it. So wouldn't it be nice to fingerprint a rogue access point before you start